Okay, fine. So, before I start my session, let me request one thing. See, make sure that you always join the teams through your Microsoft official login credentials. Okay? Don't join with the help of your Gmail or some other mail. Always join with the help of official Microsoft mail ID. Okay? So I can see that Prakash, you're there. Prakash Kambli. Prakash, you're there. Okay, so I request once again, make sure that don't join as a guest, join as with the help of Microsoft official Teams login credentials. Okay, so a very good morning, everyone. I welcome you all for the Strength of Materials lecture series with the code 18CB32. So in the previous session, we had started with shear stress numerical examples, and we have seen few numerical examples from rectangular section as well as circular section. So today we shall see few of the numerical examples for I section as well as E section. Okay. See now at this stage, you people are perfect with calculation of inertia with symmetrical I section and unsymmetrical I section, or probably even T section as well. Now, taking that into consideration, we can proceed with shear stress for an I section in a very simple way. See, I'll not go in deep now because you already know how to calculate inertia for an I section. So I'll just tell you the procedure, right? Because the concept wise, you have already done it for a rectangular section. Now, only question is how it changes for an I section, right? So which are the critical points where you are supposed to calculate the shear stress? That's what you need to concentrate. Okay. So let me stress on that first. So today's class, I will go with the shear stress calculation for a typical I section. Okay. So please observe this question. Is this question visible to you?
Yes, ma'am.
Okay. So the question as it says, an unsymmetrical I section as shown in the figure. Okay. So I'm not taking a typical symmetrical I section now because the only difference I'll tell you later what will be the differences. Okay. So I'm just explaining this unsymmetrical I section. So if you do it for unsymmetrical I section, probably T section as well as symmetrical I section will be an easier task to you. Okay. So you have basically an unsymmetrical I section as shown in the figure. It is subjected to shear force of 40 kilonewton. Right? I'll repeat, it is subjected to shear force of 40 kilonewton. So that means F is directly given to you in this particular question. Right? F is 40 kilonewton. Suppose if this F was not given to you, then probably he might have given you what type of beam it is, what type of loading it is, right? So suppose if it is a simply supported beam subjected to concentrated load at say suppose 2 meters apart, given the span of the beam, then at that stage you need to calculate shear force with the help of your SFD concept, right? So you know how to calculate maximum shear force for a given beam. So that you can use. Now that thing is not given to you directly. He has given you shear force 40 kilonewton. So maximum shear force this section is subjected to is 40 kilonewton now, right? So now with this he has also given you the cross section of I section, right? So you know, like cross section in the sense about the flange width, depth of the flange, web thickness, web depth, and bottom flange, and so on. So every cross section is given to you. So now he is asking you to draw shear stress variation diagram. So if you remember, you have done the bending stress variation diagram for I section as well as T section, right? There you had calculated only for the top fiber and for the bottom fiber, if you remember, because we know that bending stress is maximum at the top or bottom fiber and it is minimum at the neutral axis. But it is exactly reverse in The shear stress. We know that in case of shear stress, it is maximum at the neutral axis and it goes on reducing as you move top or bottom from the neutral axis, right? So that variation you need to show in case of I section as well as T section. Now in rectangular section, you already know how the variation is. I have told you. So you get a parabola, right? So of course it is a parabolic variation itself, but let's see how it goes in for I section as well as T section. Okay, so observe this carefully. This is a typical example. So if you are perfect with this unsymmetrical I section, you can easily proceed with T section as well as symmetrical I section. So you can do that. Okay, so this is a typical uh, unsymmetrical I section. I request everyone, you can hold your calculators with you. Okay, be ready with your calculators. Okay, so you can get your calculators if you want. Okay, I want everyone to answer here. So this is an unsymmetrical I section. Now at this stage, see, you know how to calculate inertia. So I'll not repeat that calculation now. We have discussed about how to calculate inertia for an unsymmetrical I section. First, locate the neutral axis from YT or YB, then proceed with the inertia calculation. So before I go to that, uh, just observe this cross section. Top flange width 80 mm. It is in mm. Okay. So unit is missing here. Kindly note. Make the correction. Top width 80 mm. Depth of the flange 20 mm. And bottom flange 160 mm. And depth of the bottom flange is 20 mm. And this web, of course, this is missing here. This web depth. Okay, so depth of the web is 200 mm. Kindly note. Let me show it here. Depth of the web is 200 mm. Okay. So this depth of the web is 200 mm. Okay. This distance is 200 mm. Rest all everything is given in the question. This is 200 mm. Okay. So this is 200. This is 20. This is also 20. Okay. And this is 80 and this is 160. Okay. Now, can you tell me what is capital D here in this case? First, what is capital D? That is overall depth of the beam. What is capital D? Overall depth of the beam. Start from the top flange and to the bottom
240
flange. What is the overall depth?
240.
mm. So capital D is 240 mm. Okay. So capital D is 240 mm. I hope this part is clear to you. Once this part is clear to you, what is your next step? Your next step is the first basic step is to locate the neutral axis. So neutral axis procedure I have already told you. So first calculate YB or YB, that is A1 Y1 A2 Y2 A3 Y3 divided by A1 plus A2 plus A3, right? So you know that calculation. So proceed with that calculation, locate YT and YB and then calculate inertia. So here I have located this YT. Of course, in the previous session, I had taken the reference from YB. You can do the same procedure. So once you get YB, you can easily calculate YT. Okay, now, so YT, I'm getting it as 140. Okay, so can you tell me what is YB? If YT is 140, we show it here. Yes, can anyone tell me? So this is my neutral axis. Okay, This is YT, that is 140 mm, which I've got it from the calculation A1Y1 plus A2Y2 plus A3Y3. So can you tell me what is this distance is equal to? YB is equal to. Fast. Take your calculators. What is YB is equal to? Y bottom. Capital D is 240. Capital D is 240. What is YB is equal to?
100, ma'am.
240 minus 140. So it is 100 mm. So YB is 100 mm. Correct? So first always mark it in this way so that it becomes very clear to you to understand. Okay, and web thickness is 20 mm. Web thickness is 20 mm. Okay, so this is a clear picture to you now about the I section. So whenever you get an I section, always make sure that first you calculate all these things: YT, YB, neutral axis depth, and capital D, and so on. Okay, so after this, calculate the inertia. So inertia calculation I have already told you. You can either write it in one single equation, or since this is an unsymmetrical I section, you should go with I1 plus I2 plus I3, which I have explained you in the previous session for bending equation. You can take that same calculation, same procedure, and proceed with that. So that calculation I have already shown it here. I have written it in one particular equation. If you feel it is a bit difficult, you can go with I1 plus I2 plus I3. Okay, that is for top flange, web, and bottom flange. Okay, so use this, that is BD cube by 12 plus A into Y bar square. Okay, so do that for all the three sections and you will get an answer. I is equal to 6805 3333.0 mm raised to 4. This is inertia of the section. Okay, so this is the inertia I've got from the section. So this calculation I've already explained you. You can note the same. Okay, so after getting inertia, always first write the formula. What you're doing here, you're basically finding out the shear stress. First write the equation for the shear stress. Okay, so first write the equation. Q is equal to F divided by B into I, A into I bar. This is my basic equation. Okay, don't go for QB first, just simply write Q. So Q is equal to shear stress is equal to F divided by B into I, A into I bar, where F is the shear force, which is already given in the question. B is the breadth of the section. I'll tell you which breadth you should take. I is the inertia, which you have already calculated. A into Y bar is, this is one of the typical things you need to understand here. Okay, now, before I go into the substitution part, let me tell you another thing where you should calculate the shear stress. Okay, so up to here, everyone has understood? Up to here, everyone has understood?
Yes.
Okay, so now, so I'll tell you few points. Okay, at that point, you should calculate shear stress. Okay, compared to bending stress, it is bit lengthier I section for the shear stress. Lengthier, but quite easy, very easy. Okay, but you need to understand at which all points you should calculate the shear stress. Okay, so let me explain that. Calculate the shear stress at top fiber of the top flange. So let me mark it. Calculate the shear stress at top fiber of the top flange. This is my one. Calculate at this layer. Okay, so you can call it as a layer or a fiber. Calculate the shear stress at, so instead of calling Q1, I will call it as okay. So first I'll calculate here at the top fiber of the top flange. Okay, so this I will call it as Q1. Okay, or else you can call it as QTF, that is top flange. You can call it as top flange. Q1, or you can take it as QTF. So here you should calculate the shear stress. Okay. Next point is this point. Next point is this point. Second one. What is this point? It is the bottom fiber of the top flange. Am I correct? Bottom fiber of the top flange. Am I correct? Yes or no? Right. So here you should calculate the shear stress. That is bottom fiber of the top flange. You can consider this as Q2. Okay. This you can consider it as Q2. So Q1, Q2. Okay. So this you can take it as bottom fiber. That is QBF. Bottom fiber. Okay, this is for top flange. These two are for top flange, Q1, Q2. Next, third calculation. Third calculation is here. Third point. Where is this third point? The third point is basically at the junction of, please observe my sentence carefully. The third point is at the junction of bottom of the top flange and top of the web. Am I correct? Concentrate on my words. Third point where you should calculate the shear stress is junction where the top flange and the web meets. Okay, that is the bottom of the top fiber, sorry, the bottom of the top flange and top fiber of the web. So it is the junction of the top flange and the web. There you should calculate the shear stress. And this is considered to be one of the crucial point where there is a huge amount of variation of the shear stress. Abrupt, you can see it as an abrupt variation of the shear stress. And these are the points where actually a section usually undergoes failure. I'll tell you why. Okay, so this is a point where a section usually undergoes failure. To concentrate at suppose if you are a designer, then you should concentrate more on these critical points. Okay, so this is a point where your shear stress abruptly changes. So here also you should calculate the shear stress. Okay, so this is the junction of the top flange and the web. Okay, so this you can call it as Q3. Okay, or else you can call it as top junction, TJ. Top junction. So however you feel comfortable, you can do that. So TJ is top junction. Next, calculate the shear stress here. What is this? Neutral axis. Am I correct? Yes. Call it as Q4 or call it as Q at neutral axis. Am I correct? Yes or no? Right. So calculate the shear stress at the neutral axis. Okay. Next, calculate the shear stress here. That is junction of the web and the bottom flange. I'll repeat, junction of the web and the bottom flange. Calculate here. Q5. Calculate it here. Junction of the bottom flange and the web. So this I will call it as Q bottom junction. Q bottom junction. QBF. Sorry, QBJ. Okay. So this is the thing. Next, calculate the shear stress here. That is top of the bottom flange. Top fiber of the bottom flange. Q6. Calculate here. Q6. Top fiber of the bottom flange. Q6. Calculate it here. Next, the last calculation. Do it here. That is the bottom fiber of the bottom flange. Q7. So all the shear stress you need to calculate for the shear stress variation diagram. I'll tell you what is the difference here. Of course, while understanding it, maybe you are feeling a bit difficult, but while calculating, I'll tell you what is the smallest difference you need to do. So it becomes very easy to understand. So before I go to the calculation part, let me repeat this where you should calculate the shear stress. And let me tell you a few thumb rules. First of all, you know that shear stress is maximum at the neutral axis and it goes on reducing as you go for the top or bottom fiber. So can you tell me what is shear stress at 1 and 7? Fast. What is shear stress at 1 and 7? First
0.
point and seventh point. 0. Very correct. So 0. So absolutely no question of calculation at all. Okay, because you know that shear stress is 0 at top fiber and the bottom fiber. It is maximum at the neutral axis, but as when you proceed to the top section, shear stress becomes 0 because there is no area at all. When A becomes 0, obviously your Q becomes 0, right? So directly write down Q1 and Q7 is equal to 0. So your calculation part is very easy now. What is your next calculation part? Either 3, 2, 4, 5 and 6. So at the 5 points, you should calculate the shear stress. That I'll explain you now. Up to here, everyone has understood? Yes? Up to here, everyone has
Yes, ma'am.
understood? Okay, fine. So let me explain this calculation now. First of all, let me write the shear stress equation. Q is equal to F divided by I into B, I into B into A into Y bar. This is my shear stress equation. This equation, you should use it for all the sections which you have written now. 1, 2, 3, 4, 5, 6, 7. Okay. So F divided by I into B into A into Y bar. Observe carefully for all these sections, for all these points, F remains same. Agree? F, I remains same. Agree? Yes or no? Shear force remains same. It is already given to you in the question. I also remains same. It is already given to you in the question. Sorry, you have already calculated. Only thing is breadth B, A into Y bar will change for all these points. So that you need to concentrate. Okay. So I hope this point is clear to you. Next, I'll come back to the Q2. I'll come back to the Q2. I'll come back to the Q2 calculation. Okay. I'll come back to the Q2 calculation. Okay, I'll come back to the Q2 calculation. See, observe the Q2 calculation. F is already given to you in the question. What is F? It is 40 kilonewton. That is 40 into 10 raised to 3. Correct? Convert in newtons. F is 40 into 10 raised to 3. Next, I is already been calculated. Use that. B. Please observe at the second point. Can you tell me what is the breadth of the section? First, at the point 2. Can you tell me what is the breadth of the section? B. Is it 80? Yes or no?
0, ma'am.
Breadth of the section at the point 2. What is B is equal to?
80, ma'am.
80.
80 mm. Very correct. So Q2. So now I'm actually Q is equal to 40 into 10 raised to 3. Okay, divided by I. You just substitute. I'm calculating Q2 now. B is, as you said, it is 80 mm into A into Y bar. Okay, into A into Y bar. So what is A? What is A now? That's very important point. What is A? See, what is A into Y bar according to you? Wherever you are calculating shear stress, top area should be considered. Yes or no? This is what we have discussed in the previous session. At whichever point you are calculating the shear stress, top area should be considered. Now please observe, if I am calculating the shear stress at second point, please see my shaded area. Is this my shaded area? Yes or no? Top area should be considered. Is this my shaded area? Yes or no?
Yes. Yes, ma'am.
Right. So can you tell me what is the area for this? Is it 80 into 20?
Yes, ma'am.
Right. So substitute A is equal to 80 into 20. 80 into 20. Okay. A is equal to 80 into 20. So you can open and bracket here. Instead of here, I'll just substitute here itself 80 into 20. Okay, A into Y bar. Into Y bar I should write. This I'll just into Y bar. So can you tell me what is Y bar now? What is the meaning of Y bar? CG of the considered shaded area. Okay, Y bar meaning is CG of the considered shaded area to the neutral axis. Can you tell me from here to here, what is the distance? Observe my cursor. What is the distance? Use your calculators.
140
See,
minus 20 divided by 2, ma'am.
excellent, very correct. 140 minus 20 divided by 2. So what is the answer? Is it 130? 130.
Yes.
Right. So answer is 130. As you said, it is 130. So close the bracket, operate this in your calculators. Now you will get an answer for Q2. Is this understood to you? Now you will get an answer for Q2. Is this understood to you? First, shear stress at second point. Do the calculation and you will get it Newton per mm square. Is this understood to you?
Yes,
Is this
ma'am.
clear? Okay, fine. So do this calculation, okay, and get me the answer for Q2 and write it in Newton per mm square. Keep it aside. Now I'll tell you the next part. Okay, now I'll tell you the next part. So I hope the second point shear stress is clear to you. Q1, first point, it is 0 as you said. Now I'll come to the third point, Q3. Okay, now I'll come to the third point, Q3. Okay, what is Q3? Q3 is the point between the junction. It is called as a junction of top flange and the web. It is the junction of top flange and the web. Okay, now I'll just tell you what is the difference. Calculation is very simple. Please understand this carefully. If it is the junction, so I am just concentrating on this layer. So this layer is very important to me. Okay, now in this layer, does F remain same? Answer to my question. Does F remain same? Shear force, yes or no? In this
Yes,
your
ma'am.
formula, F remains same? Yes. What about I? I remains same? Inertia? Inertia remains same for the entire section, yes or no?
Yes, ma'am.
Inertia remains same. Okay. Can you tell me what is B? B, only the B changes here. Can you tell me what B I should take here? Only the breadth changes here.
20, ma'am.
Can you tell me what? Very correct. So only the breadth changes in 0.3. So breadth should be taken as 20 mm. Is that understood to everyone? There I have taken B as 80 mm. Here I should take B as 20 mm because it is a junction. Are you getting my point? So breadth should be in your whatever the formula you have substituted there. You just take B is equal to 20 mm. Everything remains same. Even A into Y bar remains same. Yes or no? What is the area top of it? It is the same shaded area. So A into Y bar also remains same. Is this understood to you?
Yes, ma'am.
Is this understood to you? Okay, fine. So calculate Q3 as I have done it now. So calculate Q3 and take the answer in Newton per mm square. Okay, so I hope this part is understood to you. Now I'll come to the point. Q4, that is at the neutral axis. Now I'll tell you the calculation at the neutral axis. This is one of the important point because you know that shear stress will be maximum at the neutral axis. Okay, so now at the neutral axis. So this is my neutral axis NA. Okay, now see once again F remains same, I also remains same. Can you tell me at the neutral axis what is your B? Because your neutral axis is lying at the web. Suppose if your neutral axis is lying in the flange, then that's B you should take. But in this problem, your neutral axis is lying in the web. Can you tell me what is B is equal to? Is it 20 mm? B here. It is 20 mm
Yes, ma'am.
width of the web. Right. Right. So for the neutral axis, B is equal to 20 mm. Next, the only difference is A into Y bar. Next comes is A into Y bar. See, this is my neutral axis. Okay, this is my neutral axis. Please observe my shaded area. When this is my neutral axis, top area I should consider. See, top area means I should hatch even this. This is also my shaded area now. Am I correct? This entire thing is shaded area now. Am I correct? Yes or no? One is
Yes, ma'am.
top flange and up to this web, up to neutral axis. See, both are shaded area now. Up to here, I should consider A into Y bar. So as you said, B should be taken as 20 mm, that is one apart. Next comes is A into Y bar. Now two times A into Y bar you should consider. Why? Because one is of the top shaded area, one is of the bottom shaded area. Okay. Now, please observe this. I'll do the calculation here itself. See, this I'll take it as Q4. I'll make the correction here itself. Okay. So this I'll take it as Q4. Okay. Now I'm calculating at the neutral axis. This is Q4, neutral axis. Okay. Now 40 into 10 raised to 3 is same. I is also same. Only thing is this 20 has to be changed now. This 20 instead of 80, it will become 20. Correct? Instead of 80, it will become 20 because neutral axis, it is 20 mm. Into, okay, into A into Y bar. Into A into Y bar. Let me explain this. See, A into Y bar, this is my first part. This is A into Y bar. This remains same. A into Y bar. This is A1. This is Y1. Correct? Plus, I have not completed. Let me take another bracket here so that it is clear to you. Let me take another bracket. Okay. So this plus second area now. Okay. This plus second area. Where is your second area? See, first of all, just consider this now. Okay. Top flange, this shaded area. 80 into 20 area is same. Okay. Into Y bar. What is Y bar? Y bar is the center of this area, that is CG of this area to the neutral axis distance. As you said, it is 130. So 80 into 20 into 130. That is same, and that I have already written it here. Okay, that I have already written here. 80 into 20 into 130. Next comes is this web part. Next comes is this web part. Okay, web part in the sense. Please observe my yes. Please observe this. Yes, please observe this part. Okay, observe this part, this entire part, web part up to the neutral axis. This area into Y bar I should consider. Okay, this area into Y bar I should consider now. So only this half web part. Can you tell me what is the area? First of all, you should know what is this distance. Can you tell me what is this distance? Is it 140 minus 20? Am I correct?
Yes.
120, very correct. So what is the area for this web? It is 120 into 20. Am I correct?
Yes, ma'am.
Right. So 120 into 20. And next, mark the center point of this area. This is my center point of this area. That is CG of this area. So now from this to this neutral axis, can you tell me what is the distance? Y bar. What is this distance?
60, ma'am.
120 into 20. Is it 60? Okay, fine, very correct. So the answer is 60. So 120 into 20 into 60. Correct? Yes,
Yes,
120 into 20 into 60. So just write it here. So A2 Y2. Now I should write A2 into Y2 bar. So as you said, it is 120 into 20. Okay, into it is 60. So now close the bracket. Now your entire equation completes. Now calculate and get me the answer for shear stress at the neutral axis in Newton per mm square. That's it. So this is the Q4 calculation. Okay. So I hope this part is understood to you. Practice this. Now I'll explain the next part. Next part is once again very simple. Now I'll come back to the fifth point. That is the junction between the bottom flange and the web. This is also once again a very important point. This is the junction between the bottom flange and the web. Okay. Now, please observe this junction. So in this junction, once again, F remains same, I remains same. At this junction, can you tell me what is B is equal to? Breadth B is equal to
20, ma'am.
20, very correct. So at this junction, breadth B is equal to 20 mm, very correct. Into A into Y bar. Okay, now please observe this carefully. Here, instead of taking the top area, now I'll go in a reverse way just to make sure that my problem is easier. Either you can go top of the neutral axis or the bottom of the neutral axis, whichever you feel comfortable, you can proceed with that. But whenever you come to the bottom flange, always try to make the problem easier. So instead of going at the top part, either you can go for the top part or the bottom part, whichever you feel comfortable, easy, you can do that. So now at fifth point, instead of going at the top part, I'll just calculate this shaded area. That is also very correct. We'll get the same answer. Okay, either top or the bottom. So for Q5, take this bottom area. Okay, for Q5, take this bottom area. Can you tell me what is this bottom area is equal to? Is it 160 into 20? Q5.
Yes, ma'am.
Right. So it is 160 into 20. So I'll just make a correction here. This, I'll just remove this part. Okay. So, and here I should make the correction. This is 160. Okay. And even this Y bar is going to change. So this is 160 into 20 into Y bar. Can you tell me what is Y bar here? What is Y bar here? So this is my point, CG of this area from this
110,
to
ma'am.
neutral axis. Is it 110?
No, ma'am.
No, not 110. YB is 100 mm. So is it 90?
90, ma'am.
90. So this is 90 mm. So I can write into 90. So just calculate this. You will get an answer in Newton per mm square at the Q4. Is it understood to you? Yes or no? Is this understood to you? So not at the Q4, this is at the Q5. Is this understood to you?
Yes, ma'am.
Is this understood to you? Okay, fine. Okay. So now my last point, that is Q6. Because Q7 is 0. Now I'll come to the last point, that is Q6. Okay, that is the top fiber of the bottom flange. So now Q6. The same formula continues here. Everything is same. But can you tell me what is the only difference now? Because even the shaded area is also same at Q6, bottom shaded area. Can you tell me what is the only difference for Q5 and Q6?
B changes, ma'am.
Very correct. Only the B changes. At Q5, the B is 20 mm, but at Q6, B is at Q6,
160,
B
ma'am.
is 160. Very correct. So here I'll take it as 160. Okay. So while operating in the final exams, be very careful here because this becomes 160. That's the only difference in the entire numerical example. Okay. So be very keen in observation for Q1, Q2, Q3, Q4, and Q5, Q6, Q7. Okay. First of all, Q1 to Q7, it is 0 itself. Other calculations, you just go through it. Is this understood to you? Calculation? Yes? Yes or no? Right.
Yes, ma'am.
So shear stress at first, second, third, fourth, fifth, sixth, 7th point. Do the separate calculations, get me the answers, and then now I'll tell you how to plot it. Now I'll tell you how to plot it. Okay. And while plotting, a thumb rule, you should always have that thumb rule. What is a thumb rule? So you always note that at the neutral axis, you always get the maximum shear stress. So that you know always. Suppose if you are getting at the neutral axis, if you are getting less shear stress, then make sure that somewhere you have gone wrong. Okay. So let me explain the variation diagram now. See, this is the variation diagram I have drawn. First, draw the baseline. This is my baseline. Okay. So this is my baseline. After the baseline, Always one thing remember, first mark the points, then join the points with the help of a parabola. Why parabola? Because you know that shear stress variation, it has a term y square. So when it has a term y square, it is always a parabolic variation. In case of bending stress, you had a term y, so it is always a linear variation. You always got an inclined straight line. But here it is a parabolic variation, because so that you need to draw a curve. Okay, so first draw the baseline here. Okay, so after the baseline, go on marking the points first. So just observe here, project the lines and then draw it. Okay, so at Q1 this is 0. Next at Q7 this is 0. Next at Q2 this is Q2. Okay, that is bottom of the top flange. This is Q2. I am getting it as 1.525 megapascal or Newton per mm square. Mark it, 1.525. Next, at Q3, that is at the junction. Q3, I am getting it as 6.133. Mark it. Next is at the neutral axis. 1, 2, 3, 4. That is neutral axis. Q4. Q4 I am getting it as 10.345. So make a distance and mark it here. Mark this point, 10.345. Next, at Q5, that is at the junction. Q5, okay, no, not at the junction. Yes, at the junction. You are getting it as 1.058. Just mark it. Next, at Q6, you are getting this at 8.464. Just mark it. So after marking all these points, now simply join this. Okay, see, this is how I have joined it. Let me show it in the paint itself. See, first take the projections. Okay, first take such projections. After taking the projections, join first mark the baseline. After marking the baseline, first mark the points. Okay, first mark such points so that it becomes easy to understand. Okay, sorry, not here. So first mark such points. Okay, next simply join this. This is how I have joined now. This is at the neutral axis. Okay, from here it has been ready. Then again here, and this is how you will get the variation diagram. So this is my variation diagram, and always see that at this point axis you get the maximum shear stress, and you need to mark the values. You should write the values. Then only your answer will be correct. So this is the shear stress variation diagram. Okay. So I hope this part is understood to you. So this diagram carries 2 marks after the numerical example. Okay, so always make sure that you draw this diagram, parabolic variation, shear stress variation diagram. Okay, and also mark the magnitude. Magnitude marking is also very important. Is this understood to you? The same thing I have drawn it here. Is this understood to you? So
Yes,
now
ma'am.
make, yes, okay. So okay, now you can also make this shaded area. Okay, so quite easy. See, once if you understand the concept, and once if you get to know where at which point you should calculate and where you should take the B, that becomes very easy. Okay, so maybe it's a bit lengthy, but it's quite easy. So understand and just draw it. Now I'll tell you what is the difference between T section and symmetrical I section. See, in case of T section, follow the same procedure, but only thing is bottom flange is missing. So when bottom flange is missing, you just calculate up to Q5. That is sufficient. Am I correct? Yes or no? In case of T section, bottom flange is missing. So completely remove the bottom flange. So up to calculate up to Q5. So Q5 will be 0. Am I correct? Yes or no?
Yes, ma'am.
Yes,
Yes.
ma'am.
Right. So just remove that bottom flange Q5 becomes 0. That's it. That is the only difference. Rest follow the same procedure. And only thing is you should know how to calculate inertia for a T section, which I have already explained in the previous session. Refer that. Okay, next, another important point. I'll tell you what is the difference if it is a symmetrical I section. If it is a symmetrical I section, observe this carefully. This distance, observe this carefully, this distance and this distance remain same. Am I correct? Because it is symmetrical. Stress variation is same. Diagram remains same, but only thing is you get a symmetry because your section itself is symmetry. Suppose if it is unsymmetrical, then this distance and this distance is gonna vary. Am I correct? To do this, give a try, you'll understand what is the difference. Okay? Rest all the procedure variation diagram is as usual, and another point is for a symmetrical I section, you should know how to calculate the inertia. That is also another point. Okay, next, the very important point is I said that if you are a designer, okay, you should be very particular about the junction. This junction, concentrate here. This junction, these two junctions are one of the crucial points. These are the points where you can observe a usual failure of the section. Why it is so? Because I'll tell you why it is so. Because please observe the shear stress variation diagram here. Okay, observe the shear stress variation diagram at the junction. See, at the junction, let me show it here. Okay, see, at the junction, observe this carefully. At the junction, first it was 1.525. What is 1.525? It is the shear stress. It is in megapascal, Newton per mm square. At the junction, first it is 1.525. And once it has entered the web at the same position, abruptly the stress has increased to 6.113. Am I correct? At the same line. Yes or no? First, it was 1.525. Once it has entered the web, it has gone to 6.113. So at the same line, abruptly the stress has increased at the same point. And that's why this is called as one of the crucial point or the critical point. We call it as a critical point because at here, abruptly the stress is going to vary because of the junction. Because you can see that cross-sectional area, very immediately the cross-sectional area has been reduced at the web. Because of this, the junction should be taken care of if you are a designer. Is this understood to you? Yes?
Yes,
Even
ma'am.
you can observe it here, right? So even you can observe it here, this junction. Here it was, this is the point and this is the point. Abruptly the stress has been increased at the same line. So always junction should be designed critically. Okay, so this is about the I section. So T section and symmetrical I section, this is an assignment to you. I'll give you some assignment questions. Okay, I want everyone to practice. Procedure remains same and I have told you what is the difference for the T section. Okay, so give a try. If you face any difficulty, we'll discuss this. In the next class, we'll continue with the new concept, that is the torsion. Okay, so in the next class, we'll continue with the torsion chapter. Okay, so this about the T section, I want everyone to practice. If you face any difficulty, you can contact. Okay, so that's today's session.
Thank you.
Thank you, ma'am.